in the use of human language in computer science, there's a spectrum between a widespread use of extremely simple models, in particular the bag of words model. So actually at Carnegie Mellon University, they have this wonderful art installation that you can see a picture of there on the left of. They have the bag of words, which is a lovely thing. But it's very commonly we just sort of say what words are in a document and just use that. At the other end of the spectrum, if you go and look in linguistics, that it's commonplace in linguistics that people are using incredibly complex and nuanced representations of linguistic structure, which by and large, most computational people feel aren't useful and haven't attempted to implement. But what I'd like to hope and want to argue for today is that there's space in between those things for some basic linguistic structure that's helpful for natural language applications. And so if I take one more moment of inspiration from linguistics in the recent work of Noam Chomsky and colleagues, that they've wanted to argue that a central factor of human language is that it has the property of recursion, and that's basically it. So if I generalize just a little bit from there, the theme that I'm going to concentrate on today is the idea that if you want to understand complex things like language, you have to be able to understand the parts that they're made up of and how those parts then combine to give the more complex wholes, such as this diagram here of a Ducati engine. And so my basic argument is that artificial intelligence requires being able to understand bigger things from knowing about smaller parts, doing composition. Of course, that's not the only thing it requires. It also requires other things like planning and knowledge, but this is a big part of what we need to have. And so that's something that I've concentrated on in my own work in deep learning. I know in this hackathon you're hearing a bunch of talks from different people on deep learning, but a particular interest of mine has been how can we not just have word vectors and word representations, but how can we get beyond that to know when larger linguistic units are similar in meaning. So we'd like to know that a snowboarder leaping over a mogul is similar in meaning to a person on a snowboard jumps into the air. And how do people do this? Well, they interpret the meaning of larger text units by doing semantic composition of smaller elements. We start off knowing what words mean, and then we can put them together into phrases, including for phrases that we've never heard before. And so there's been a lot of work on representing the meaning of words as vectors in a vector space, and that's been an incredibly successful approach to lexical semantics. And I was interested in the idea of, well, how do we get beyond that and have representations for the meaning of longer phrases? And the hope has been maybe what we could do is find a way to take these longer phrases and also give them a meaning inside the vector space. And the question is then how we might go about doing that. And so the idea that we developed was what we will actually do is semantic composition in a fairly linguistically motivated fashion using the principle of compositionality. So we'll determine the meaning of a phrase or a sentence by taking the meanings of the components that make it up and then have a composition function that can combine them together, and then we'll get the meaning of a phrase or a sentence. And this I've mainly motivated and will mainly motivate from the point of view of language, but it's important to realize that this idea of composition applies in many other places as well. So when you understand a complex mathematical formula, well, you'll tend to do that compositionally. You recognize the front part's a normalizing term and the right-hand part also has some more structure to it. And when we look at visual scenes, well, visual scenes are also composed between smaller pieces that go together to make up the whole representation. And so the question is, can we then build these kind of meaning composition functions in deep learning systems? And what I'm going to do today is, in the first part of this talk, tell you some of the work that we've done on deep learning meaning composition systems. And then the second part, I'm actually going to show you some non-deep learning work exploiting some other ideas from natural logic, which have also been centered on this idea of how to do composition in natural language. Okay, so for the deep learning part, we built a sequence of models that are in the space of tree recursive neural networks. So when we want to build up the meaning of a phrase, what we're doing is taking the meaning of its components, putting it through a neural network, and then we're getting out of that a representation of the meaning of the phrase, and perhaps sometimes a score of its goodness as well. So more concretely, what we're doing is we have vectors for the words. We're putting them through a neural network, which in the simplest case, version 1 here, we're just concatenating the two vectors, doing a matrix multiply, adding a bias term, and then putting that through a tanh nonlinearity, and that's then giving us a representation of the phrase. This was the very first model that Richard Socher and I came up with back in 2011, and it started us off in this direction. In retrospect, it wasn't a very good model. There was only a single weight matrix in the whole system for the composition of everything. And if you think about this model a bit more, since we just concatenate the two words here, you can think of the two parts operating separately. So there's kind of like there's a W1 and a W2 that multiplies each part. So the two words and their meanings don't really interact together properly. And so I'd argue that this pretty clearly isn't adequate for a human language composition function. But it was already enough to get us some nice results, and then it was a starting point for more complex models. And I want to go on and sort of give you a quick survey of some of the other models we went through and then concentrate a bit more on the more recent ones. So moving on from there, we had the idea that, well, a simple way to get a bit more power would be to have the composition function depend on what kinds of things are being composed. So a verb taking an object would compose differently from an adjective modifying a noun. And we thought that that could be a neat idea for building a parser that was better. So there's been considerable success with using straight symbolic context-free grammars for basic syntactic structure when used in a probabilistic context-free grammar context. But it seems like those models can model the syntax of a language pretty well, but not really the semantics and the meaning as to what should modify what. And so the hope was that what we could do is we could take phrases of a particular type, B and C, which have a vector representation, and so then when we combine them together, we're still using the same kind of simple neural network to do the composition. And the difference, though, is that the weight matrix is specific to the kind of categories that we're joining together. And this actually worked quite well to improve the performance of the Stanford parser in our continuous vector grammar parser. And a nice thing about it was that the semantic models could actually learn something about where meaning is conveyed in words. And so one way you could see this is it learns what are the heads of different constituents. So if it's joining a noun phrase in a conjunction, it knows that the noun phrase carries most of the semantics of that. Whereas if you're joining a possessive pronoun like her or its with a noun, it realizes that most of the meaning can be found on the noun side, and that's stuff that can be learned automatically. But still, we wanted to get further than that and have the idea that the meanings of words really interacted with each other when you did linguistic composition. And so trying to think about how to realize that, our next idea was to turn to matrices. So what we want to model is if you have something like very and good, that its meaning just can't be it's very and it's good. Rather, very modifies the meaning of good, and so it produces a stronger version of good. Whereas if you had something like not good, not modifies the meaning of good and takes you to the other end of the spectrum. And in conventional semantics, you do that in lambda calculus by making very a function that takes good as an argument and modifies its meaning. And if you think about that in vector space terms, it seems like the natural way to do that would be to have a matrix that can then modify the meaning of a vector. Because in general, it wasn't clear which functor and which side was going to be the argument, what we did is said that each word is going to be represented by both a vector and a matrix. And then when we combine the meanings of words, we're going to create a new vector for the phrase, which is done by multiplying the alternating matrix and vector parts, multiplying that by a weight matrix, and then putting it through a nonlinearity again to get an output representation. And then also we would build a new matrix for the phrase, and that would be formed from the matrices of the kids multiplied by another weight matrix. So again, this was a model in which we could actually get some neat results. So one neat result was we could use this as a model of relation extraction. So we wanted to learn particular relationships, so that in my apartment has a pretty large kitchen, that kitchen is a room, a component inside the apartment, and similar relations of the kind that people extract relations of something being located at a place and being spouse of and things like that. And so we were doing that for putative entities connected by a relation, we're computing a representation of the node that joined them and then putting that through a softmax classifier to decide what relation held between them. And this we were able to do really rather successfully. So these charts compare previous results on this system, on this task, which was a SemEval task from 2010. And what we found was that our previous basic tree recursive neural network sort of worked okay. I mean, much better than the simple SVM, not as well as the very feature-rich models that people had explored before. But the matrix vector RNN worked much better. And then by starting to not just use word representations, but a few features of our own, we could sort of push up the numbers to beat the best previous system, but using a lot less hand-coded features than in the system that's represented here. So that was nice. On the other hand, this matrix vector RNN model was in many ways very problematic when you looked at it more closely. And a lot of the problem was with these matrices. So firstly, matrices just involve a lot of parameters which are hard to estimate well. We dealt with that to some extent by just shrinking the size of our vectors, so that if we shrank the vectors to length 25, the matrices were only 625 elements. But that was bad in another way, since it's generally known now that bigger word vectors normally work better for tasks. And we didn't really have any good way to pre-train the matrices for words, so we just randomly initialized them, and our ability to compose their meanings was fairly weak. So if you looked at the matrix representations that they were able to learn, they weren't actually very successful at representing a good matrix that could multiply to modify the meaning of another word. And so what we were then looking for was, could we come up with a different way where word meanings could closely interact without requiring the huge number of parameters of the matrix vector model? And so that led us to develop the tree recursive neural tensor network. And so the idea of that is that, well, a very simple way to have two words meanings interact would be to say, well, let's just take their dot product. That's an interaction that's sensitive to word meanings. But that only produces a single number back. And so if we wanted to do more than that, we want to get out a vector of numbers. And well, a way we could do that is we could generalize the dot product a little by sticking a matrix in the middle. So that would still produce a single number back, but it could be mediated by the matrix to be a more general composition operation. But if we then replicated that unit the number of times as the length of the vector, which is equivalent to putting a three-dimensional tensor between the two vector representations, then the result of this vector, three-dimensional tensor vector multiplication would be to produce another vector of the same size as our word representations. And so that was the idea of our neural tensor layer. We combined it with our previous layer, so we had both a multiplicative relationship and the old concatenative relationship. I'm not actually sure if this part on the right is very necessary, but we can made in the models we built. Okay, and a place in which we showed the utility of these models is whether a piece of text is negative, positive, or neutral. So in many cases, sentiment is quite easy. So for long documents, you can sort of just count up the positive words and negative words and have some simple bag of words classifier. So for long documents, you can commonly get 90% sentiment from bag of words methods. But for short pieces of text, it's harder. And so if you look at something like sentences from Rotten Tomatoes movie reviews, you get sentences like, with this cast and this subject matter, the movie should have been funnier and more entertaining. Well, this has positive words like funnier and entertaining, but you're meant to decide that this is a negative statement. And so how might you be able to do that? So we thought that one of the problems was that there just wasn't actually adequate data to be working these kind of things out. And so, oops, that didn't work. So one thing we did was construct a sentiment tree bank where we actually took phrases and of sentences and asked Turkers to judge them for sentiment. And so we actually have for whole sentences their different parts of their structure and whether it's positive or negative. And that actually gave us a richer source of supervised training data for training models. And it allows us to train and test for what meaning compositions look like. So having this richer source of data actually helps all models, that even if you're just building a naive Bayes bag of words model, its performance goes up significantly when trained on this data because you can separately train it on each phrase that has a sentiment rating. So the naive Bayes model is much better able to work out what are positive words and what are negative words. Somewhat worryingly, our existing neural network models, when trained on this sentiment tree bank, actually work no better than a naive Bayes model trained on it, which showed us we had some work to do. But fortunately, we had this new idea of the recursive neural tensor network, and it provided a more powerful model. So by using it with both its multiplicative and additive representations, we were able to train this model over the tree structure, training all the weights jointly with gradient descent. And this model then worked considerably better. So we now got a model that's working at least sort of 3% better than these other models. And we could look at it and we could see it doing interesting things. So here's an example of it working on the sentence. There are slow and repetitive parts, but it has just enough spice to keep it interesting. And you can see the model is able to detect that this first part of the sentence is negative, the second part of the sentence is positive, and when the two parts go together, the whole sentence ends up positive. And it works much better on these kind of sentences than any of the preceding models, which really can't tell apart successfully the different parts of sentences and how they combine. Another good illustration is from looking at negating of negatives. So you can strengthen negatives incredibly dull. What happens when you negate negatives not dull is that a negated negative becomes a mild positive. It doesn't really become good, but it becomes sort of okay. And if we look at the different models that have pre-existed, when you had a negated negative, all of the preceding models basically said negating a negative didn't change its rating at all, which partly reflects the fact that negation by itself is kind of negative. If you don't use negatives if you want to sound a positive person. But the RNTN is able to capture that negating a negative makes things more positive, if not very positive. So that was great, and we were very happy with that. Our happiness dissipated a little over the next year because a couple of people at Google, Kwokler and Tomasz Mikolov now at Facebook, then developed this model called the paragraph vector model. And the paragraph vector model is sort of a glorified word-to-vec model where it has an extra representation it learns to represent each paragraph, but it doesn't make any use of syntactic structure. And they showed that they could get their paragraph vector model to actually work considerably better than our recursive neural tensor network model. So that sent us back to the drawing board. But last year, we came up with an even better form of tree composition model, which picks up the idea of using long short-term memories. So in sequence models, people have had enormous success in deep learning by using long short-term memory sequence models. And so it occurred to us, well, maybe we could take that same neural composition unit and then apply it to tree structures, and maybe that would allow us to do even more accurate tree composition. And so Kai-Sheng Tai started working on that idea. So the idea of LSTMs is that when you are stepping through a sequence, you have these extra gates which are themselves worked out by neural networks, but have a probability come out of them which says how much to use different things, how much to pay attention to the input, how much to use the internal state in deciding the output, how much to remember from one time step to the next. And particularly these forget gates tend to be very central to the operation of LSTMs. So we wanted to use those and then combine it with the structure of sentences to keep the same ideas of tree-structured composition. And so that gave us the tree-structured long short-term memory networks. And so what we're doing is when we have a constituent like the tall tree, it has a head word tree and then some children that are dependents, the and tall. And so these would go in as multiple pass states, which would have forget gates each attached to them. And the head word, the tree, would be the input, and it would create the next unit in the LSTM, which would then continue to climb upwards. And in this way, we could generalize an LSTM to any branching factor, so that we've got the head word of a phrase being the input, and each of the other dependents would then be going in as if it was from the past via a forget gate. And our LSTM model can selectively decide which parts of which of the different children it then pays attention to in doing composition. So nicely, this actually worked, and it worked not only considerably better than our previous model, it worked at least a little bit better than paragraph to vector, and it also, interestingly, a lot of recent work in deep learning has just used sequence models for language, and they've actually been quite successful. But I think one of the nice results of this work is we have a good comparison between just using a sequence LSTM and a tree LSTM, and we actually are getting significantly greater value from using the tree LSTM structure. So this is just doing two-class sentiment, positive versus negative. We also have results from doing finer-grained sentiment, where you're precisely trying to work out how positive or how negative different statements are. And in this configuration, we're actually getting bigger gains from the tree LSTM structure. So that actually seems a pretty good model, which we've then started to use also in other contexts. As well as using it for sentiment, you can also use it for other tasks. So this is working out semantic relatedness using the 2014 SemEval task SIC. And again, the tree LSTM works better than a simple LSTM and better than the various other methods that were entered into that SemEval task. And so here's just one visualization of a tree LSTM at work, where the whiteness of these forgets are then saying how much attention is paid to different nodes. And you can see it's correctly deciding that you want to remember about waste and you want to remember about good, but when these two combine together, it's waste that dominates, so this gets a negative rating.